Okay. Hmm. The second type of problem is set packing problem. Okay. There are two sets, S and U. S is all the sets to be packed in, and U are all the elements. Okay. Uh, Now, such kind of problems you will find uh, in logistics more often. Okay. Let's say that you have a lot of packages. Let's say Amazon has a lot of packages. Okay, and it has three different trucks. Okay, and there are 100 different packages. Now the question is, which package should go to which set or which truck? Okay, that is a question. Whether a truck is chosen, okay, and which package is assigned to which truck. Okay, so this is a set packing problem. There is a slightly different approach for this called bin packing problem, but this is more or less similar. The parameter aij, this parameter will tell you whether a particular element belongs to a particular set. Okay, uh, and here in the same way we loop through all the elements j. Okay, and for each set we sum up uh, for all the aij, all the j's that are active, uh, all the i's that are active, all the sets that each particular j belongs to, that aij will be one. And in this way, this constraint will make sure that you have all the sets. There is a cost of each set being active. So let's say one truck, this a particular truck is being used. Okay, there's a cost associated with that truck. Uh, and if you want to maximize or minimize the cost, in this we want to maximize it. We want to make sure that as many uh, the total cost is as much as possible to assign to each set all the elements that are required. Okay. Xi is the binary variable here. Okay. Example is given now, maximum number of non-overlapping projects to fund, but it is the same that I mentioned as before. Okay. Knapsack problem. Knapsack problem is there almost everywhere. You want to find out the best set of elements that you want to pack in a bag of 15 kg weight when you go to the airport. So everybody who's trying to pack their bags and bring it onto the airport and fly is trying to solve a kind of a knapsack problem. Okay. In a knapsack problem, we want to maximize the value of all the items that we are trying to pack. Okay. A very good example would be, let's say that somebody tells you that you can, this is the basket, this is a supermarket, you can buy as many, you can take as much stuff that can fit in this basket and you can take it home. Okay. Now, as a consumer, you know that this is a very good opportunity to buy as expensive stuff as possible. So you will have three parameters in this case. Okay, you have I set of items. I is all the items that is present in the supermarket. Okay, xi is basically a variable that is indexed over all the I, uh, explaining whether or not you choose that item. There are three types of parameters. One is the value of that item. Okay, what is the cost of that item? Some item would cost rupees 10, some item would cost rupees 100, and so on and so forth. Okay, but that is not the only question we have to ask about the item. We also have to know whether the weight, whether uh, the particular basket can carry it. Okay, so each item would have some weight associated with it. So this is a sort of a capacity constraint. Okay, and W is the maximum capacity of the knapsack. Knapsack in this is the capacity of our basket. Okay, okay. So in this basket, we would add as many items as possible. Okay, so that we meet with all the, yeah, we meet with the capacity. We don't exceed the capacity, and we maximize the value. Okay, we want to maximize the value that we want to correct connect in this problem. Okay, this is very similar to the previous problem. Just here we have only one set. In the previous problem, in the set packing problem, we could have multiple sets. Okay? We would have multiple knapsacks. Here there is only one knapsack, and this is the way you define the mathematical model. We have vi xi, some or all I. We want to maximize it, subject to wi xi less than equal to w. Okay, this is the weight constraint. Okay, uh, if somebody is new to mathematical optimization, or somebody is new and somebody is not able to guess or visualize a problem that is given, what one should do is they should go through all the common types of optimization problems that are present, and I've written almost all that I could find. Okay, if you get a gist of all of these problems, just by looking at the equations you will be able to tell what how the problem is in real life. Okay, uh, and it is very important to be able to visualize this. Okay, that is the reason why we are going through all the common types of problems, so that we can easily write a new type of problem when we need. So in reality, any problem will be a combination of all of these classic optimization problems. This I plan to take in the third part. In the third part, the problem that I would choose, I will make sure that most of the uh, standard problems we have covered uh, can be we can describe that problem using all these standard problems. Okay, okay. The third, and I think one of the most important problems in mathematical optimization is a traveling salesman problem. Okay, and this, if somebody is new to this, I think they should really pay attention and try to understand this problem, because almost all complexity in the world is seen. Uh, all computational complexity is seen and understood uh, based on this problem. Okay, and I'll quickly try to give an example. Let's say there is a person X. That person has three friends, A, B, and C. These people live at different locations on the map. So if we think about a map, these are the points on the map, on the graph for X, for A, for B, and for C. Now, X needs to visit each A, B, and C and come back home. Okay. In this case, let's say in the first scenario, X only has to visit A and B. What are the different ways X can go? X can go A, B, first to A's house and first to B's house. Then X can go from B's house to A's house. Okay. And of course, coming back home is just coming back home. Okay. If X also, we also considered C, then it will be A, B, C, A, C, B, B, C, A, okay, B, A, C, C, A, B, and C, B, A. Okay, so this this enumeration will tell you the complexity. So if we have just two nodes on the graph, we have two combinations. If we have three nodes on the graph, we have 1, 2, 3, 4, 5, 6. 6. Okay. Okay. So just based on this, can anybody tell me what complexity this means as n grows? Okay. N is the points on the map. I. Okay. Cities. Okay. Uh, how will the complexity grow as we increase I? I'm sorry, Dr. Veerababu, I think you were saying something.
Grows exponentially.
Yes, exponentially. But exactly what is the uh, formula? What is the, sorry? Factorial. Yes, factorial. Somebody also messaged factorial. Yes, so it grows by factorial. And how do we see that? Like, for example, if there are two nodes, 2 factorial is 1. If there are 3 nodes, 3 factorial is 6. The same way, we can go to 4 factorial, 5 factorial, 6 factorial, and so on. And this problem becomes so complex when, even when there are 10 cities. Even if you have 10 cities, then the problem becomes 10 factorial, and 10 factorial is a very big number. At around 25 to 30 factorial, we will have more uh, paths, or more uh, uh, path for a salesman than there are atoms in the universe. Okay, so this very seemingly simple simple problem, which seems very simple, you just want to minimize the distance, you want to go to each friend, you want to come back, and you want to find such a path, you will have so many such paths which minimizes the distance. So dij, the total dij will be minimized. In this case, okay, just beyond 10, 15, no solver will be able to solve it. Okay, and this this kind of problem is found everywhere. A vrp is a type of tsp, is a special kind of tsp. Okay, we can even find it in scheduling problems where you have like changeover setup time. Okay, how do we write this problem? In this problem, there's one major constraint that I did not mention. Okay, uh, so here the first constraint is basically making sure that each j that goes from I is visited. Okay, each I is visit each I that is going to a j uh, should be should be one. Okay, and each, so this is like saying, let's say I1, I I2, I3. Okay, and this is j. So this is like saying exactly one of them should be active. Okay, okay, and the other is in the same way but in the opposite direction. Every I that is connected to all the j's, exactly one of them should be active. Okay, let's say this is active or this is active. Okay, there is a subtour elimination constraint that I don't want to go through right now, but that is a very important constraint if somebody wants to deal with TSP. I'll go through that later on. Okay, vehicle routing problems are described in the same way. Here, along with the customers, we also have a set of vehicles, and it is like saying that you have all these nodes. Okay, not only you have to find the path of least distance, but you have to find many paths of least distance for each vehicle. So here, one more dimension is added to the variable, or one more index is added to the variables, that is vehicle. So in this case, you have cities I, j, and vehicle k. Okay, so each path is now defined by a vehicle. So this is k1, this is k2, and these are all ij's that are active. Uh, let's say this is k3, Okay, and this is K4. Okay, so this can be written in the same way. I won't go in more detail, but the model can be written in the same way, except one important constraint for all this, for each K, for each K. Okay, the capacity of the total capacity of vehicle should not be exceeded. So we add at each customer what is the quantity that you pick up. Okay, so QK. Yeah, so QK is actually weight of each customer. Let's say, yeah, yeah. Okay, so we make sure that the total capacity of all the vehicles is not exceeded. So basically, this is just summing of all the W's of all the customer that we want to pick up in the vehicle. Okay, assignment problem. Assignment problems are also found everywhere. Even a Sudoku can be written as an assignment problem. Although Sudoku is more of a constraint programming problem, it's not an optimization problem. You don't want to minimize any set of assignments, but it can be written as an assignment problem. At least we can write the constraints in the same way. Assignment problem is the same. We have two sets of indices. We have tasks and we have agents, or we have tasks. We can have tasks, or we can have machines. Basically, which agent does which task, and this kind of problem can be seen everywhere. Every time we book an Uber, or we book uh, or we order food through a door delivery app, we have this assignment problem taking place. So when we order food, every 5 minutes, uh, what the algorithm does is it searches for all the people that are available to take that order. Okay, and it finds the best person that can bring you that order, based on the ratings, based on the distance, and that is the assignment. So every agent I and task J, in this case task I and agent J. Okay, okay, if we choose it, it's one, or if you don't choose it, it's zero. Okay, same way we have cost. Parameter would be cost of assigning each uh, task to each agent. Okay, and definitely one agent can do only one task. There could be case in there could be reasons why you would want to assign two tasks to an agent. That can also be done, in which case you can say less than or equal to two. Okay, for example, there are cases wherein the Swiggy delivery person carries two orders at the same time, and he delivers two orders at the same time from a restaurant. So we could use a constraint like this. Okay, next is network flow problem. Network flow problem is very similar to a TSP problem. Okay, we want to minimize the cost of each arc. Okay, but here it's not the distance, it is the cost on each arc. Okay, and it doesn't have to come back, it doesn't have to circuit. So network flow problem is a TSP without a circuit. Okay, let's say, okay, here are two nodes, and we have to explicitly show in a network flow problem which nodes are connected, which nodes can be connected. So let's say 1, 2, 3, 4, 5, 6. Let's say there is a connection. Let's say there is a connection like this. There's a connection like this. There's a connection like this. Okay, and there's a connection like this. And same way, there's a connection like this like this, and like this. Okay, so here it would be 1, 3, 1, 4, 2, 3, 2, 4. Okay. If any of the 1 3 or 1 4 is active, then any of the 3 5 and 3 6 should be active. So I'll write the rest: 3 5, 3 6, 4 5, 4 6. Okay. Let's say that 1 3 is active, meaning something is going inside C3. If something is going inside C3, by a flow in the network, we want to make sure that something is coming out of 3, because that's how a network flow works. So if 1 3 is active, then we have to make sure that 3 5 or 3 6 would be active. Okay, the same goes on the other direction. If 2 3 or 2 4 is active, then and something from 3 is going to be active and something from 4 is going to be active. Okay, this particular constraint says that. So generally here it's supposed to be 0 actually to balance the mass. Okay, let's assume that it's something like this, 0. Okay, so in this case we are saying that everything that is coming to I, okay, everything coming from I, for each I, everything that is coming to J and everything that is going out of I should be equal. Okay, so it's like it's saying something like this. Okay, okay, and this is ith node, and all J are coming to I, all the variables for which J are coming to I, and all the variables for which I is going from I is going, it's going to J. Okay, we are saying that exactly one of them is active. Okay,
Sir, sorry to interrupt you. In that case, if it is not zero, if bi means something will be left at that node or what?
if it is not 0, yes, we can assume that.
Okay.
Yeah.
Okay, sir. Thank you.
Okay, let me go through the scheduling problem. Such kind of problems are again everywhere. Each of these problems, we will find innumerable examples in real life. And I mean it. Okay. Timetable, daily timetable of school. Okay, that is a scheduling problem. Jobs and machines. If we replace machines by teachers, okay, it becomes a scheduling problem. And jobs by lectures, this becomes a scheduling problem. Okay. Uh, an important uh, point is there are different types of scheduling problems. There are discrete time scheduling problems and there are continuous time scheduling problems. Discrete time scheduling problems are those where we have fixed lecture hours. Let's say that each lecture is of 1 hour and it is fixed. A continuous time scheduling problem is where it's not fixed. It can start at any time and it can end at any time. The first lecture can start at 12 a.m. and it can end at 3:35 12 p.m. and it can end at 3:35 p.m. Okay, this kind of problem is called a continuous time optimization problem. Okay, and the next lecture could start at 3:35 and could end at 4 also. Okay, so these quantities are not fixed. Okay, the distance between two start times and end times is not fixed. Okay. Okay, so there are two types. Here I've taken a simple example of a discrete type problem. Okay, uh, Okay. Generally, the most important objective is to minimize the make span. Okay, we want to say that we want to have the minimum amount of time in which the whole schedule should be complete. Okay, and this is the best way to write that. There are many ways, people write it in many ways, but this is the best way. So the largest start time, okay, is also included in this, and because each each start time can only start after previous job's end time. Okay, so if you see here, the first one, okay, what it says, this is the start time xi j. Okay, start time for machine I for job j. Okay, this is the processing time, and this is j plus 1, job plus 1. Okay, if the next job is getting processed, it will be after the previous job start plus the processing time of the previous job. Okay, this is the end time of each job j. Cj equals to xij plus pij. Okay, this is saying cj should be less than equal to the complete time horizon dj. Okay, or the deadline of the complete jobs. Each job might have a deadline. We want to make sure that it is less than that. And xij, okay, is basically a discrete start time. This we have to say that it is greater than 0. Okay. Okay. Facility location problem. These are solved every time there is a hub and spoke mechanism to your problem. Uh, there are a few examples in the repository. One is the Amul milk supply chain problem. So basically, what happens in a milk supply chain? We have all the farmers, the milk farmers, who bring it to the milk in Amul milk cooperatives. There are, let's say, in Gujarat, there is a village which is a milk cooperative. So hundreds of farmers will come from different places and give milk and sell milk to this milk cooperatives. So there will be many milk cooperatives. In Gujarat, there are many villages where there are milk cooperatives. And each village, each district has a processing unit, a milk processing unit. Okay, a processing. Let's say this is a processing unit. Okay, a processing unit, milk is sent within 50 to 100 kilometers because we don't have much time. We have to package it and then sell it. Okay, maybe sell it in the form of packets everywhere in the 200-kilometer radius. Okay, so here, which processing unit should get milk from which village cooperatives of Amul? That is a facility location problem. Okay, because this processing unit will definitely have a capacity. It can only process a few tons of milk a day. Okay. Now, from where should we collect this milk? We want to collect this milk so that the distance from each cooperative is the least. There are many factors involved. There are GST involved. There are places where farmers get or the cooperatives get GST rebate and stuff like that. So all the uh, nitty gritties are involved in real life, but the problem is more or less the same. We want to find those sets of those combinations of the facility, in which case this is the processing unit or processing facility, and all the nodes from where the milk is brought to the capacity facility. So we have to choose all of them. Okay, and this variable is very similar to the other variable where xij. Okay, in this case, okay, I is the facility here. Okay, and j are all the you village cooperatives. Okay, there could be a case that some facility is not being used at all for some reason. Maybe all the capacity, we don't need to start this facility at all. Whatever demand we need is taken care by this facility itself. Okay, and that is why Another binary variable is needed, yi. Okay, so if you see here, till now, just one variable was enough to describe the problem. Okay, maybe scheduling we needed more variable, but before that, almost everywhere we needed one variable, and the indices were two or three. In case of a vehicle routing problem, we had three indices where the third index was the vehicle. The two indices were almost always the same in either network optimization problem or the traveling salesman problem. The I and the J index where going from a particular node to a particular node are the same. And this is also that kind of a network problem. One of the indices is I, another index is J. Now, uh, each variable which is connecting ij, whether a particular I gets inventory from a j, is one variable. Here we are also having another variable yi is whether or not a particular facility is active in itself. It could not be active. Okay, uh, in real life, a facility, to set up a facility, there is a fixed cost. So every time a business wants to set up a new facility, and this happens everywhere, we want to expand the as you know, the GDP is growing by 7% of India. At the same time, the number of products that we are selling in the market is also growing. So because we are selling more products in India, we have each of the industries is getting new facilities. Okay, Zudio is a very good example. If somebody is from India, you will see that Zudio has 2 years back there was news that it has bought so many warehouses because they are they have to keep the stuff that they manufacture somewhere before they bring it to the retailers, and where they have to keep it is a very big strategic decision to be made. Okay, we have so many options. We have thousands and thousands of candidates where we can use those warehouses, but we will only choose those warehouses which will give us the least cost over the years. Okay, and choosing such variables means solving a mathematical problem. Okay, we could guess, but in real life, it happens that we run such problems. I personally have uh, built such models for a lot of industries, including airline industries or cement industries, etc. uh, One thing that I quickly want to mention, that once you see a math problem, all you have to do is find real life problems that already exist that you can quickly think of. So this is just a blueprint to expand somebody's thinking who does not know math models. Okay, and you see a model like this and you just think about all the problems that you can fit in this model. Even clustering is kind of a facility location problem where you want to cluster different uh, points on a map. Okay, portfolio optimization. Um, this is an assignment problem where you want to find the best portfolios. Uh, the, I'm sorry, this is not exactly an assignment problem because there's only one portfolio. If you had multiple portfolios, then it would have become an assignment problem. But it's very similar to an assignment problem. You are given a set of all the assets, and you want to choose those assets and the investment in each of the asset which will maximize your returns and minimize your risks. Okay, the most uh, the biggest example is Markowitz optimization. Okay, um, xi in this case is a continuous variable. Okay, representing the proportion of each asset that you want to choose. Let's say that you have three options: Tata Motors, ITC, and Mahindra and Mahindra. Okay, now you want to you have 1 lakh rupees. You want to find out how much you should invest in each of these to maximize your returns. Okay, let's say somebody told you ITC does not grow as much as Tata. Maybe, I don't know, but At the same time, it is not as risky as Tata, because the car market is changing quite a lot, but the tobacco industry market does not change much. Okay, so one would have more reward, but another would have less risk than the other one. And the objective is to, I'm sorry, this is not visible properly. Okay, uh, yeah, expected RI. This is how it should look like, and XI or all I. Okay, this is what we want to maximize the returns. Okay, we want to maximize the returns. There is also a required return. We want to make sure that we want to make sure that the returns are more than this. Actually, the model can be written in two ways. One, you want to maximize the return. Second, you want to minimize the risk. There is another way you can write the same model. Okay, minimize the risk. If somebody wants to minimize the risk, that means they want to minimize the covariance. They want to make sure that um, um, that is there is less variance between all the assets that we have chosen. And yes, the one of the most important, the total asset, the proportion should be one. So maybe 33% of Tata Motors, 33% of ITC, and 33% of Mahindra and Mahindra. So this is one or 100% of the complete. Okay. We could have multiple ways of representing this. We could say that we want to minimize we want to make sure that the risk is not more than 5%. Okay, in that case, instead of return, here we would have risk, uh, and we would capacitate the risk on the total investment. Okay. Next is a bin packing problem. Uh, Actually, this would happen more often when we are packing a bag. Okay. Uh, Bin packing problem is a feasibility problem, but a knapsack problem is an optimization problem. What do I mean by that? Uh, in bin packing problem, you have to worry about the space. In knapsack problem, you have to worry about the weight. Okay. A bin packing problem is more spatial in nature. You have a truck and you have boxes. Let's say all of them are square boxes. How will you place of different shapes? How will you place these boxes that you fit in maximum number of boxes inside the particular truck? Okay, let's say that the truck looks like this, and you have many boxes that you have to keep on the truck. Okay, and you want to make sure that you maximize the number of boxes that you keep. Okay. Okay, I'll quickly go through how the model looks like. I is set of all the items, in which case all the boxes. B is set of all the bins. Okay, bins can be different trucks. Okay, Xij is whether a particular item I is placed in bin J, and Yj is whether a particular bin J is used. So in the same way, whether a particular truck is used and whether which item is assigned to which truck. Okay, there are parameters like weight of item I and capacity of bin J. So here, for ease, we have taken weight, but a more complex problem is volumetric assignment in bin packing problem, where you have a 3D way of determining where to keep which item, so on and so forth. Okay. Now this capacity is pretty much similar. If Yj is active only, then a particular Wj, the total capacity of bin, is constrained on all the Xijs, all the i's assigned to that j. Okay, and we take W, weight of all I, to sum more all the weights. Uh, and we minimize the number of bins used, so minimize the number of trucks in this case. uh, you see, a vehicle routing problem can also be a bin packing, can also be partly a packing problem. Let's say, sorry, hello, is my hello, is my screen still visible?
Yes, yes.
Yes. I think we have only 10 minutes left, and these are more than enough problems to discuss in one call, I think. Let's move ahead to questions. We will discuss some things in detail, what we want to talk about, and then in the next one, partly I will take constraint program, and partly I will try to try to build an optimization problem, or how uh, we can build it uh, uh, in real life. We'll go through. Okay, so if there are any questions.
Sir, I don't have any questions, but seriously, I don't know about this. I have heard about this portfolio optimization, but and this is this thing I could able to know from this lecture, and yeah, I'm looking forward for more lectures.
Okay. Perfect. Sure. Thank you. I am, there's a lot of content, and I will try to cover as many as I can. I get only time on a Saturday. But yes, if I get feedback on what kind of problems and so on and so forth, my objective is to try to build a community where we develop such problems, uh, and build solve such problems together. So yes, thanks a lot.
It's great.
Yes, yes, I have shared the complete PDF uh, in the Discord channel.
Atul, one doubt.
Yes.
This bin packing, na, it needs some more constraints to be added, or this is fine? Because right now for the model it goes for 0. Oh yeah, fine. Okay,
Yeah.
down.
Yeah. There's only actually in most of the problems I've only taken a few constraints just to show how it is. Um, but yeah, basic bin packing problem will have only these two. Yes, I will share the link to the Discord channel for whoever is present today. I'll quickly show the Discord channel.
Just a couple of questions. So first,
Yes.
just talking about the bin packing problems.
Yeah.
More from a logistics delivery point of view. So suppose if we need to add constraints in terms of uh, the the luggage that had the parcel that has to be delivered first should be placed towards the rear end of the vehicle,
Hmm.
things like that, and also the orientation of the bins, etc.
Yeah.
So how do we build on that? Just if you can touch upon that.
Yeah.
And the second thing is that since we are recording these, will you also be sharing the link for the recordings?
Yeah. Yeah, actually, currently there is no problem, the kind of problem that you're talking about in the GitHub data. But what you're saying is a very complex problem to solve. Okay, as easy as it looks, it is very complex. Okay, like the first thing that you mentioned, I'll just quickly try to go there itself where we did it. Yeah. Okay, like the first one which you mentioned, Akshay, is yes. The package which goes first should have a higher priority. Okay, generally how these things are done is, we let's say this is a bed of a truck. Okay, generally I have seen even in papers is they have these slots on a truck. Okay, and these slots are made based upon the item size and shape, and you have each item and where on the path. Like let's say that you already have a path, like this is a path, these are all the nodes on the path. Okay, and uh, the items which are supposed to be delivered on path, for, on the beginning of the path, should be on slot number 5. Let's say there are 5 slots from inside. This is the starting of the truck. Okay. So truck is facing this way. So you have 4. Let's say currently there are 4 slots. So we will define things like that. Like if we have 20 items and each item can be 5 items can fit on a slot. So we can define slots like that, and we say that, uh, put this item on this slot. Okay. Now comes the second question of how to place one on top of the other. Now the problem goes into 3D bin packing, and yeah, it is exactly as complex as it sounds. Actually, it is.
Yeah. So basically, yeah, no, I was talking about the horizontal orientation, but when you brought it to this figure, I also had a thought regarding the vertical orientation as well, like what you spoke about 3D window effect.
Yeah.
Basically, some items can be fragile,
Yeah.
so we cannot place anything above on top of that. And
Yes.
from a delivery point of view, also when the truck is going out to deliver,
Yeah.
regarding the horizontal that we just discussed, that some items need to be placed towards the rear end because the the delivery person needs to go and find them inside, right? So I mean, basically in the order of the delivery, they can be horizontally placed, and also in terms of agility, they
Yeah.
can be vertically placed. So
Yes.
yeah, just wanted to check that whether we do take care of this in terms of like post, like pre-processing of data, or basically do we can add some constraints in terms of the model population to account for this.
Actually, generally, it's a good idea to do it inside the model itself. Such kind of models can be solved using constraint programming very well. Now, which is on top? Like, let's say a good example that you gave was fragile item. Fragile item should always be on top of any other item. Let's say like there is a rule, something like that. Okay. Um, and let's say that we have a mapping on top or on bottom. Maybe there is a variable. Okay. So if it is a fragile item, it will always be on top. You know. Uh,
Yeah.
yeah, we can have such variables, and like each orientation might have take a different space. So if this item is oriented like this, like if a guitar is oriented in uh, like along its length, if you're keeping it, then it will take a different space. But if you're taking it around its breadth, then it is taking a different space. You know what I mean?
Okay. So basically, we'll be defining a variable that will tell the
Yeah,
geometry and all.
that defines the space it will take for each orientation that you have.
I see. I see. That's
Yeah. These, I mean, you will find for bin packing problem, big, like uh, research on all of these types, like the ESO. That's the this is the fun part. Like each of these small basic problems they are so complicated in real life that uh, you can find like people have tens of years of research on just something like this. But yes, if you have a problem like this in real life, please share it. We can, sort of find something that we can work on. You know,
absolutely. And about the recordings part, so
recordings.
basically your recording session. So where can
Yeah.
we find the link to the recordings?
Yes, yes. I will share those. I will share those on the same uh, Discord channel.
Got it.
So there is a Discord channel. Okay, it's called Deep Dive. I have added this PDF there. I will also share all the videos, links to all the videos there itself.
Sure.
Any other question?
One thing like Atul, like as Akshay said, like if we are adding more constraints, then we have to go for these commercial solvers like Cplex or Gurubi, right? So are you going to discuss those things in the coming lectures?
Um, yes, actually, I am going to. I've taken examples of all the different types of solvers and
Okay.
scale also. Also,
Okay.
there are many examples.
Yes, yes.
So definitely, this is a very vast space, and a lot of people I know who have built up and a lot of code also for large scale problems. Yes, we will discuss. And also, I will also I'm adding more content is basically what kind of problem, okay, and what scale of problem, and generally what technology, what technique we should use. Okay, let's for example, um, bin packing problem. If you have only 50 bins and it is only two-dimensional, okay, and there are no complex constraints, then you can solve it using a math model. Okay, if uh, it is a 3D bin packing problem, I'm just giving an example, and there are these constraints, then you have to solve using CP. Otherwise, you can solve using dynamic programming. You know, like how uh, so each of the problem for each of the scale for all each of the type of the problem, we have different approaches to solve it. Actually, I mean, generally there are. This is the best approach. You know, saying something like that.
Yes, yes, correct.
Yeah.
Thank you.
So we will also cover that in the future. Okay. Anything else? All right. So no more questions. Thanks a lot, guys, for attending. I'm trying to build this content and build upon this and have a meta content that I can share easily on different platforms. So this has been really helpful. I'm getting a lot of questions. I'm getting a lot of feedback and understanding how it is going on, and it is a learning experience for all of us. Thanks a lot for attending and being a part of this group.
Thank you.
Yeah.
Thank you.
Thank you all.